We're now recording, and I'll turn it over to Brennan.
All righty. Well, thank you guys for coming out, whoever is coming. And if you're watching this later, welcome to the next meeting. This is our next edition of the Zoom Talk series. And today we have Dr. Ethan Siegel today, and we are super excited to have you. Just a little bit about him. He got his undergraduate degree from Northwestern University in physics, classics, and integrated science. And then he later got his doctorate in astrophysics from the University of Florida. Like he mentioned earlier, he has a blog that he does 5 days a week. He does podcasts once a month. And he's just an overall very active member of the science community. And if you want to add anything else to that, Ethan, go ahead. And otherwise, go ahead with your talk.
Sure. I mean, I'm a real person too. I have a website at startswithabang.com if you want to see all the stuff I do. One of the things you might like is every year I put together a new elaborate cosplay, and I've got maybe the last 15 years of cosplays documented on the site. So back before you were old enough to dress up for Halloween, I was, being willing to put it up on the internet. So I've been blogging since 2008 was when I started. So I've been doing this, like many things, it started as a side hustle 14 years ago. And I wound up leaving my full-time job as a professor at Lewis and Clark College here in Portland to be a science communicator full-time. And so I'll just, say that to encourage any of you. If you're like, oh my God, like I'm 16, 17, and I don't know what to do with my life, that's okay, because there's a good chance that whatever you'll be doing 20, 25 years from now, that job doesn't exist yet. And that's okay. When you go and you learn what you're interested in, you're going to be growing your mind, you're going to be developing skills, and whatever you go on to do in life, no one's ever going to be able to take that away from you. The things you learn, the things you know how to do, that's going to stick with you forever. So, believe me, I get plenty of people who, when they want to criticize me, they're like, look at this guy. He hasn't written a paper in however long. He hasn't published in however long. He hasn't done whatever. Those aren't people who are my colleagues. People in the field, they're like, no, Ethan knows his stuff. He knew his stuff 20 years ago. He knew his stuff 10 years ago. What makes you think he doesn't know his stuff now? So, don't. There are always going to be haters. The more successful you get, the more haters you're going to attract. Never let them get you down, and always know that the people who will criticize the loudest are usually the ones who are producing the least. And with that said, there is one thing I want to let you guys know is I am right now working on a project called the Encyclopedia Cosmologica. And this is a new book that I'm going to be working on with a couple of legendary space artists, one of whom was the primary artist for Carl Sagan's original television program, Cosmos. And we're putting together a illustrated history of the universe where with every page that you turn, you're going to step forward 100 million years at a time. And I'm just so excited to have, I've been calculating how many stars and galaxies and planets with life should there be in the universe at this time. And I've been writing the text for what happens during the first 100 million years and the second and the third and so on until you get to the 138th and get to the present day. So it's a lot of work, but I do enjoy it. All right, well, with that said, hopefully I'm going to have a screen sharing permission here. And let's see, can people see this screen?
Yes.
Sweet, that's what I wanted. So my talk today is on the topic of where did the universe come from? And let's see if pushing the space bar will move me forward a slide. It does not. All right, let's see if pushing the left arrow or the arrow. Nope. All right. I bet you there's a clever way to do this. Why don't we just, what if I hit here? What are you? Oh, that didn't work at all. All right. Hooray for technology. Oh, what about you, page down? Oh, yeah. Oh, yeah. Yeah, man. I used to be the one who would tell old people, like, ah, come on, how do you not know how technology works? And now I am that. It'll happen to you too. All right. So, of all the questions that we can conceive of about the universe, think about it, right? The grandest one of all is you can ask is, where did it all come from in the first place? And this isn't easy because if you want to know where anything comes from, the first thing you have to do is know what it is. If you don't know what the universe is, you are not going to be able to tell me where it came from because you don't even know what it is. How could you know where it comes from if you don't even know what it is? So, on the one hand, that's what we have to do. We have to go out, look at the universe, measure it, and actually identify what is it. The second thing we have to do is we have to understand what are the underlying laws and rules that govern it. What are the laws of physics, right? Because that's the whole thing that allows us to make predictions is we have to say, okay, I'm going to set up my system like this, and I'm going to have some physical system. And then I have rules and laws that apply to it. And what do those rules and laws tell me? Well, they tell me that if I start with a set of initial conditions for my system and I apply the laws, then I know what that system's going to be doing in the future, right? So the laws of physics, if you understand them well enough, you can calculate the outcome of a physical system that begins with a set of initial conditions. It's only from those starting points that we can identify the possible avenues for how could things have gotten to be the way they are today. You have to know what they are like today, and you have to know how the laws that govern the universe work. And that's what we want to do, because then we can come up with, like, all right, what if I start with this scenario and I evolve it according to the laws of physics? What predictions do I get out? That's how we do it. That's how we play the game, is you say, okay, I'm going to come up with a scenario. I'm going to apply the laws that I know. And what do I predict would come of that if this is correct? The ones that agree with what you observe and measure, those are valid. The ones that don't, those are invalid, and you chuck them. So that's it. Now, here's the thing that I think is remarkable. No matter when we are in the universe, no matter where we are in the universe, if we take that scientific approach of we look to the universe to see what it's like, and we learn the laws of physics, and we try and say, okay, what happens when I put these together, we would get the same answer every time. It wouldn't matter where we were. It wouldn't matter when we were. If we did the investigation correctly, we would get the same answer. And that to me is like one of the most remarkable facts about science. So today, we've pushed the frontiers back incredibly far. We know where planets come from, where stars come from, elements, atoms, and more. We have overwhelming evidence for the hot Big Bang, and even information that takes us before that instant of creation. And I'll tell you about that. So if you're like, huh? Like, I'll tell you about it. Don't worry. But despite all that we do know, there are some unknowns that have no solution at present, and that maybe would be even impossible to figure out in principle. And that's a heady thing to think about. So let's get into it. All right. Today, when you look out at the universe beyond the limits of Earth, right? If you're lucky, you'll see something gorgeous like this, right? Even in Portland, I don't think you're going to get skies like this. But if you go out towards, like, there are places like an hour away. If you head like an hour east of Portland, you can get some real dark skies pretty fast. And you might be able to see sort of detail in the Milky Way like this. Now, when you look out at the universe beyond the limits of Earth, you get a pretty comprehensive picture of what's out there. We can start to answer where all of this comes from just by looking at what is all of this, right? You don't ask people, right? You don't ask poets, where did all this come from? You don't ask theologians, you don't ask philosophers, where did all this come from? If you had a big existential question, hundreds or thousands of years ago, that's who you had to ask. But people are notoriously unreliable. So what we do is if you want to know something about the universe, you ask the universe questions about itself. That's like the most basic thing there is about science is you don't ask people what they think. I mean, you can if you want to entertain their wild thoughts, but the big thing is you ask the universe questions about itself. You set up your experiments, you make your observations in the laboratory of the universe, and the universe tells you what it is and what it's like. So let's start here, right? This is a beautiful site of the Milky Way, but it's taken from planet Earth. And our planet, like pretty much every other planet in the universe, is made of atoms. We have a gaseous atmosphere, we have a solid center, and at the center of Earth are the densest, heaviest atoms. As you go out, you find that Earth is layered and that you have lighter, less dense layers floating on top of the denser layers. This is a fun fact that I don't know if you know. If you were to take a look at like the biggest mountain ranges on Earth and measure the Earth's crust, you would find that, yeah, you don't just have the biggest mountains, but that the crust is also the deepest there. The crust extends the farthest down into the mantle. Just like if you see an iceberg and you see a little bit of ice sticking out of the top, you know that there's a lot more ice underneath. Same with Earth's crust. The Earth's crust is thinnest over the deepest parts of the ocean, and the Earth's crust is thickest over the heaviest mountain ranges, not because the Earth comes up so high, although it does, but because the Earth goes down so deep. The crust goes down deep into the mantle. Everything is floating. Like this idea of buoyancy, it applies to the whole Earth too. The thing is, this works for every planet. For every dwarf planet, for every moon, even the gas giants we think have that same structure just underneath this giant hydrogen and helium envelope. So planets, now that we know what they are, they float freely through the galaxy, they orbit stars, and stars are things that get their energy from fusing lighter elements into heavier ones. When they run out of fuel, when they're done fusing the elements, the light elements in their core, what the core does is it starts to contract, right? You fuse elements together, it gives off radiation, that holds the star up. When you start to run out of fuel, the core contracts, but when it contracts, it heats up. If it can heat up enough, it'll start fusing the next element. If it doesn't, the star says, I can't get hot enough now. It's the end of my time. I'm going to become a stellar remnant. Sometimes it's gentle, sometimes it's cataclysmic. So let's see. Right, so that's a cutaway of the sun. Inside the core is where almost all of the fusion occurs. The surface of the sun, 6,000 Kelvin. To get nuclear fusion, you need to get to temperatures of 4 million Kelvin. So when the sun, when you get far enough inside that you get 4 million Kelvin, that's where you start to get nuclear fusion. But the center of the sun, 15 million Kelvin. So we're moving right along. We're moving right along, pretty solid. All right. On larger scales than stars and individual solar systems, stars are grouped into galaxies. Galaxies clump together into groups. And sometimes groups clump together into clusters, and you get even larger superstructures. All together, you wind up with this giant structure. Oh, come on. What are you doing to me, slideshow? Help me out. I just want to show this picture. All right. Well, it's not going to let me, so fine. We'll just do that. Anyway, there was a nice photo of the cosmic web here. Let me, you know what? I bet you I could just delete that guy. There we go. Look at this nice cosmic web. Beautiful, right? Hooray, cosmic web. All right. So what you get is you get this web-like structure where along the little filaments of the web, you have galaxies where you get the nexuses of the web. You get these big galaxy clusters, and in between, you have these regions known as voids, where you really don't have any stars or galaxies. The biggest one we know of is hundreds of millions of light years across, that you will just have empty space for nothing, for like no structure there, for really, really large volumes. And yet all of it is governed just by these real simple, straightforward laws, right? Come on, what are you doing to me? Well, anyway, we'll just pretend this is working. So that's what the universe is. If we want to know how the universe got to be this way, we have to apply the laws of physics to it. And that means we're going to follow the evolution of any physical system. So I can say, okay, I know how gravitation works. We have the laws of general relativity. And so wherever you have mass or energy, you have the phenomenon we know as gravitation. You say, okay, this mass and this energy curves the fabric of space, and then everything moves through that curved space, and that's gravity. You know how electromagnetism works. Wherever you have an electrically charged object, whether it's in motion, whether it's at rest, or an electromagnetic wave like a photon, you have the electromagnetic force. You also have the nuclear forces, where quarks and gluons bind together to make protons and neutrons bind together to make atomic nuclei, and unstable nuclei will radioactively decay. And anything that you start off with, if you tell me, here's your system and here are the conditions, if I know the laws of physics that govern them, I can say, here's how it's going to evolve in the future. If it's a classical system, I can say, here's what it'll be. If it's a quantum system, I can say, here's the probability distribution of what it's going to be. So I think all in all, pretty good stuff. So now that we know, okay, universe is largely made out of atoms, normal matter, planets, stars, galaxies, even larger structures, where did it all come from, right? So let's start someplace familiar, right? Periodic table, right? Everything's made out of elements. Here's the weird thing though, right? We look at Earth. Earth is teeming with elements. It has complex, differentiated, even intelligent life. We have atmosphere, oceans, that layered interior. But when you say what atoms is Earth made up of? Well, in order, Earth is made up of iron, oxygen, silicon, magnesium, sulfur, nickel, calcium, aluminum, and everything else combined is just 1.2% of the Earth, right? So you have 8 elements that make up 98.8% of the Earth, and everything else, including some stuff we think of as pretty important, like carbon, like nitrogen, like phosphorus, all of it is in that combined 1.2% extra. But what I think is interesting about this is all of these elements that I listed are not hydrogen and helium, right? In astronomy, we don't think of things the same way chemists think of things, right? If you're a chemist, you're like, oh yeah, like I have my alkaline metals and my alkaline earth metals, and I have my halogens and my noble gases and the transition elements over here. No, astronomers, we have hydrogen, we have helium, and everything else we call a metal. And that is literally how we do it in astronomy. And you would say, why? Why would astronomers be so, why would you group things this way? And the answer is because if you were to take a census of all of the atoms in the universe by number, about 90% of them would be hydrogen atoms. About 9-point-something% of them would be helium atoms, and less than 1%, everything else combined, less than 1%. So the stuff that we think of as making up our planets, that's super the minority of the universe. In fact, even if you did it not by number of elements, but by mass, only 1 to 2% of the whole universe by mass would be atoms that aren't hydrogen and helium. 98 to 99% are hydrogen and helium. So that's a messed up thing. But that teaches us something right away. If you want to make a planet like Earth made out of rocks and metals and ices and complex molecules, you have to have some way to make these heavier elements. And then you need to gather these heavy elements together in one place in sufficient abundances to form planets. But that is exactly what the universe does. So how does it do that? Well, you have stars and they go through their life cycle. And if you have a relatively low mass star like our sun, it's going to burn through its hydrogen. It's going to turn into a red giant. It's going to burn through helium in its core. Then its core is going to contract. It'll try to heat up, but it won't get hot enough to fuse carbon. So what happens is something like the picture you see here, a planetary nebula. When a star becomes a red giant, right, nuclear processes occur. It develops strong winds, which starts to blow off some of the outer layers of the star. And if the star is like the sun, it's going to die in a planetary nebula, blowing off the outer layers back into interstellar space, where they can help participate in future generations of star and planet formation, while the inside contracts down to a white dwarf. But you can also have more massive stars than the sun. And what's great about more massive stars is they die spectacularly in supernova explosions. And they live for very short periods of time, right? There's an expression that anyone who's seen the movie Blade Runner, which is probably none of you because you're all too young, might see one person who'd be like, I saw Blade Runner. They say this line that goes, the flame that burns twice as bright burns half as long. But for stars, it is way worse than that. If I were to take two stars and one star is twice as massive as the other, the star that's twice as massive will live only 1/8 as long. A star that's 10 times as massive will only live 1/1000th as long. The lifetime of a star in general goes as the mass cubed. So these really massive stars, stars that are tens or hundreds of times the mass of the sun, they only live a few million years before they burn through all of the fuel in their core and go supernova. And if you took a notice over here, you will see that these color codings on these elements are because they're produced in different ways. Some of them are produced in supernovae. Some of them are produced from when large stars go supernovae. Some of them are produced in these fusion processes that are in large stars. And some of them are produced when the remnants of stars, like white dwarfs or neutron stars, collide with each other. If you have anything made of gold, the majority of gold in the universe comes from colliding neutron stars. And that is something we only learned in 2017. So some of this stuff is really brand new stuff. All right. This is a map of the Milky Way. This is Gaia, the European Space Agency satellite's map of the stars in the Milky Way. And if you look at this, it's kind of interesting because if I were to look at the stars towards the center of the galaxy, I would find that overwhelmingly, they have more heavy elements than the sun in our solar system does. And if I look at the stars in the outer halo of the Milky Way galaxy, they have much less. They have much more hydrogen and helium, much less heavier elements. This is why, because where you have more stars and more gas and more material to form stars, you get more and more generations of stars. They live, they die, they give rise to new stars. They live, they die, they give rise to new stars over and over and over and over. Where you only have this happening a few times, you don't get enough heavy elements to make rocky planets with a chance for life. where you do have it happening over and over again, I don't know. I wonder, do we have better chances at life towards the galactic center? Are we like as far away as it gets where we have it? These are things we're still trying to figure out. But my point about doing this is when you look at the stars that are forming, there are plenty of them in the plane of the galaxy and towards the galactic center that get these heavy elements very easily. And when they form stars, right? So you have these star forming regions that, you can see all the hot young stars in here, where you see this blue color. If ever you see blue in a nebula like this, that's what we call a reflection nebula. You only get these very blue, very hot stars when you've just recently formed them, because when you form stars, they come in all these different masses. And then you sit around and you wait for a few tens of millions of years and all the blue ones die because they don't live long enough. They're too massive, they die, leaving only the red ones behind. So when you see this blue color, that tells you I have a reflection nebula with hot blue stars. I've only formed stars very recently in there. And that's kind of interesting because when we look around some of these young stars, we find these protoplanetary disks around them. Like we can actually image these disks in both infrared and radio light. And sometimes when we see these disks, we find that they have gaps in them. And we believe these gaps correspond to protoplanets that have sucked up all the material around them in the disk. So we know we are witnessing planets form. And this is also brand new. It's really only over the last 10 years that we've been able to image these at all. And now we have hundreds of them, and we want to image tens of thousands of them, which I think is pretty exciting. But inside these disks, we find gaps, we find clumps, we find other evidence of these young, newly forming planets. So you have generations of stars that live and die, new generations of stars. When they're rich enough in those recycled processed materials, they can give rise to planets, including rocky ones, with the ingredients for life. And then you say, okay, well, if that's where planets comes from and stars is previous generations of stars, then where did that come from? And where did the first generation of stars come from? Well, like I said, look at the universe. So let's look out, right? This is what we see when it comes to nearby galaxies. These are galaxies that look kind of like Milky Way galaxies, right? They're large, they come in spiral and elliptical shapes, they're heavily grouped and clustered together, they have low star formation rates, they have large masses, they have relatively low amounts of gas, and more red stars than blue stars. But as you start looking farther and farther and farther away at these more distant galaxies, here are some things we notice. The farther away a galaxy is, the less evolved it is. It's smaller, it's lower in mass. It's bluer. It has bluer populations of stars. We see that as we go back in time, because you look far away and it takes light time to travel to your eyes. You see something a million light years away, and you know it takes its light a million years to travel to you. Because the universe is expanding, it gets more complicated than that. When you look back in time 13 billion years, you're actually looking back 28 billion light years away because the universe expands. It's messy math, but the whole point is the farther away you look, the farther back in time you're looking, you see that galaxies were forming stars faster. They had more blue stars. Things were more gas rich, and you had fewer heavy elements. So that's something you see. Right? So what does this tell us when we start looking back at these distant galaxies? They're going to appear smaller also, but another interesting thing is every atom you probably learned this, that every atom has its own unique spectral lines, right? Atoms are nuclei and electrons around them, and atoms can move up and down, but only in certain energy levels. So when they do, they can emit or absorb light only at specific wavelengths. Now, what's interesting here, you can see all these lines, all the emission lines, all the absorption lines. But what's fascinating is look at these features. Look in particular at this little feature here. Notice that for this close galaxy, this feature is towards the left. For this more distant galaxy, it's farther to the right. And the more distant I go, the farther and farther away it gets. Why? Because as light travels through the universe, this is light, it has a wavelength. As the universe expands, the wavelength of the light traveling through the universe stretches. So the more you find this light is stretched, or what we call red shifted, because red is longer wavelengths, so it's shifted towards the red. The more you see that, that tells you the more the universe has expanded since this thing emitted its light, and the farther away it has to be. And this is fascinating, because why would it be doing this? The only way it can be doing this when you fold in general relativity is if the universe is expanding. So light redshifts, the universe expands, and what happens to something as it expands and as it ages? If it expands and as it ages, what's it going to do? It's going to get less dense, right? Because you have the same number of particles, but expanding is more volume. As more time goes by, gravitation is going to make things get clumpier. And as your wavelength of light stretches, it gets lower in energy, right? The wavelength of light is what determines its energy. As you stretch it out, you go lower energy, so the universe cools as well. So this tells us that as galaxies grow and evolve over time, means if I look back early enough, I could find a population of the first stars and galaxies. And before that, I shouldn't have any stars or galaxies at all, right? So I should see earlier on in the universe, it should be less dense. It should be denser, but less clumpy. I should see that I can only develop these big structures on big scales once gravitation has had time to clump everything together, so that the universe will only develop structures like galaxies, galaxy clusters, and the cosmic web according to the rules of gravitational growth in an expanding universe. That there will be an epoch where the first stars and galaxies form, and before that, all I had was gas. But I can imagine going back farther and farther and farther to where there are no stars or galaxies. And I can imagine having things get hotter and hotter and hotter the farther back I go. At some point, the radiation was so hot, its wavelength was so short that I couldn't have neutral atoms. Anytime I would have an electron bind to an atomic nucleus, if the wavelength of this photon, of this radiation, is short enough, if it's high enough in energy, as soon as it sees that electron bound to that atomic nucleus, it's going to strike it and ionize that electron. So there should be a time in the distant past where the universe was all in ionized plasma, and then it cooled, and I made neutral atoms for the first time. And at even earlier times, I can imagine I couldn't have even bound protons and neutrons together, because the energy of that light was so high that anytime I did, it would blast that apart, and I just have free protons and neutrons. This is not some fairy tale. This is the story of, this is what the Big Bang is. So we say, oh, look, I had a plasma where photons would scatter off of electrons, and I'd have electrons and atomic nuclei, but now things expand, 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 and at some point, the wavelength of these photons gets long enough that I can form neutral atoms and the photons aren't energetic enough to ionize them anymore. So I should see this leftover radiation. That radiation was predicted back in the 1940s and was discovered by accident in the 1960s. People had a new antenna, a new radio antenna. They were pointing it at the sky and they were like, what's going on? Everywhere we point the sky, we've got this low hum, this background of radiation we can't get rid of. They tried everything. They tried recalibrating their instruments. They tried pointing it at the ground and then back at the sky. They tried cleaning the horn out because there was a nest of birds living in there. They cleaned the nest out. They got the mops out and swept up the bird dung. And guess what? The radiation was still there. They had discovered the leftover glow from the Big Bang. In fact, if any of you have this ancient technology of a television set with the old rabbit ear antennas, you might know you can set that to channel 3 and you just get that static. About 1% of that static comes from the Big Bang. If you cooled down your television set to close to absolute zero and you brought it to interstellar space and you looked, you would get about 1% of that snow because you can't get rid of it because that's the leftover glow from the Big Bang and it's everywhere. You can also say, ooh, right? If I had neutrons and protons early on, I can start fusing them together to make the lightest elements. And so you expect, oh, if I could find this early population of gas, this gas from before when any stars formed, then maybe I can see what was in it. What did the universe look like when it was pristine? 2011, we discovered our very first population of pristine gas. Now we know we know of 3. We have 3 clouds of gas that are pristine now. Amazing that we even have 1. We have 3. And we see lots of hydrogen, lots of helium, tiny amount of lithium, element number 3, and nothing else. That's it, which is amazing. All right, this is where it's going to get fun now. So you say, great, these predictions have been verified along with others. What else have we found? Yes, we found that leftover background of microwave radiation. It's only 2.725 Kelvin above absolute zero. We've detected evidence for that first pristine clouds of gas. We've even indirectly detected the leftover background of neutrinos and antineutrinos that was made in the Big Bang, because they leave an imprint on the cosmic microwave background and on the large scale structure of the universe. And we have measured it so well that we can actually account for the signal of neutrinos in there, and they exist. And we also know, based on the fact that we have a clumpy universe, that the universe had to have been born with seeds, with the seeds of what would become the large scale structure. You need regions that are born overdense and regions that are born underdense. So where did they come from? This is the fun part of the game, is you say, okay, like I learned where planets, what they're made out of, and they had to have arisen. So what needed to have happened to make planets possible? And then, okay, stars, same thing with that. And then the Big Bang, okay. And so you keep building upon the last step and you say, well, now what? I had this hot, dense, expanding universe full of matter and radiation, but it had to start off with these overdense regions and these underdense regions that would grow into the structure I see today. What could have caused this? Well, there's this brilliant idea. This idea is relatively new, which is to say it's younger than me by like 2 years. This idea is called cosmic inflation. And it basically said, okay, look, I need to generate these seed fluctuations in the universe, but there are also properties about the universe that I can't explain. If I look out at the universe in this direction, I can look back in time close towards the Big Bang. And if I look in this direction, I could look, 13.8 billion years ago back towards the Big Bang. Over there and over there, two opposite directions, why do they have the same temperature in those regions? If you put a space heater in the corner of the room and you go stand in the other corner of the room, it's going to take a while for the room to all reach the same temperature because signals take time to travel. Even in the universe, things are limited by the speed of light. So if something's over there and something's over there, and they couldn't have communicated with each other at the speed of light, even by today, why do they have the same temperatures? Why do they have the same properties? So there are a few other things. Why is the universe, right? It could have been shaped like anything, like a sphere, like a saddle, like a donut. Why is it flat? Why does space appear flat? How come it doesn't appear to have any curvature to it? Right? These are things that you can say, yeah, we don't know. It was just born this way, right? If you're old enough to know who Lady Gaga is, right, you can give the Lady Gaga answer and say, yeah, universe was born this way. No, we hate that. We hate doing that in physics because that means giving up. If you say it was born this way, that these were its initial conditions, then that just means you're giving up on there actually being a physical reason why this happened. So there's this brilliant idea called cosmic inflation. And all it says is that before you had the hot Big Bang, before you had matter and radiation filling your universe so that when it expands, it gets less dense, what if instead you just had a universe where you had energy inherent to the fabric of space itself? Then what that means is as time goes on, your universe is going to inflate or expand in all directions. And then when that same amount of time has passed, if it doubled from first step, it's going to double again. But so now instead of being one thing by one, it's 2 by 2 by 2. And then another thing, it's 4 by 4 by 4. And then another time interval goes by and it's 8 by 8 by 8. And you know how exponents work. It's
Ethan has frozen.
5 meters.
Oh, okay.
And expand it to be bigger than the observable universe is today, more than 10 to the 28 meters, which is amazing. But inflation, if that happens, it also says, oh, look what else we get out. It means that if we started with a universe that was very curved, but it stretches and stretches and stretches, then when I wake up today and I look outside, what I see, I can't distinguish it from flat. It's sort of like if I said, hey, go outside and take a 10-foot by 10-foot square and tell me whether the earth is round or flat. You don't see enough of the earth to know that, right? If all you see is this little tiny patch of it, you can't know. Well, same thing for the universe. Even if we say like, oh my God, my whole observable universe is over here, this is tiny. It's too small to see any curvature. So it might be curved, but the reason it wouldn't be is because inflation stretched it flat. Similarly, I could say, ooh, imagine I had this tiny, tiny region and I inflated it to be enormous. And now here's my universe today in the middle. And I look out in this direction, this direction, this direction, and I see everything's the same temperature. Why would it be that way? Because the universe was all connected, but then it inflated. But what I love the best about inflation is it generates these fluctuations, right? You know that quantum mechanically, the universe is not this quiet place where nothing happens. If you go all the way down to your little quantum scales, you have these fluctuations that happen in space itself, right? Normally, they're so small that you don't care about it on your big scales. But during inflation, if space is growing and growing and growing, then you get these little fluctuations and they get stretched across the universe. And when they get stretched across the universe, they get joined by new ones and new ones and new ones. So you add up all of these fluctuations on all of these scales, and that's what you get today. And that's going to show up as these imperfections in the leftover glow from the Big Bang. And that's going to show up as these initial seed fluctuations that grow into stars and galaxies. And what's remarkable to me about this is that inflation makes very specific predictions for what these fluctuations should look like. And it made these predictions back in technology to observe them and test them until 20 years later. And that's what we saw is, oh my God, according to the theory of inflation, what happens? We create these fluctuations and they make the seeds of the structure that we have. And these fluctuations would have been almost the same magnitude on all scales. We would make them on scales bigger than the cosmic horizon, which means scales larger than light could have traveled since the start of the hot Big Bang. It means they would all be adiabatic fluctuations, which means entropy would be constant. And it also predicts that there should have been some maximum temperature to the hot Big Bang, that things couldn't have gotten arbitrarily hot, that they had to have heated up and then cooled down. And everything we see is consistent with that. But now that's the problem, is you can go all the way back to inflation and ask what happened before that. But I get stuck because all I know is, well, here's the biggest scales I can see my universe on today. So I can go back and back and back to maybe, to the last 10 to the minus 32 seconds of inflation and say, yep, that's what is still imprinted on my universe. But what came before it? That's the puzzle. Because of the nature of inflation, it by necessity will wipe out any information that existed in the universe before inflation happened. In fact, we can only ever hope to access what occurred during that final tiny fraction of a second of inflation. Anything that occurred earlier will be inaccessible because it got inflated away beyond the limits of our observable universe. So we can state where our observable universe came from the end of inflation and the start of the hot Big Bang. We can explain the origin of so many things within the universe. Where did the cosmic web come from, and galaxies and groups and clusters of galaxies and stars and planets and, all of it. But where did these more fundamental things come from? Where did space, time, energy, or the laws of physics in the first place come from? We don't know. Whether they came into existence or how they came into existence, these are questions that remain unanswered. All we know is that there was one instance here where we are, where inflation happened and ended. And that gave rise to our observable universe. And we live in a portion of that. And that's it. Are there other universes out there? Maybe. What happened before inflation? Did inflation have a beginning, or did it go on forever? We don't know. Unfortunately, and this is one of the mind-boggling things to me, the amount of information that exists in the universe that we can observe, the number of particles is finite. The distance we can see is finite. And the amount of time we can look back is also finite. So we don't have an infinite amount of information. The things we can learn are large, but finite. And so when I say, okay, where did the universe come from? This is the best answer we can give today. But we can ask questions that we still don't know how to answer. Why is our universe filled with matter, but not antimatter? Why we have dark matter and dark energy, and what are they? Why do the fundamental constants of nature have the values that they have, and not any other value? These questions might someday be answered, but there's no guarantee that what exists in the universe today, what's left over in the aftermath of the hot Big Bang, there's no guarantee that what remains in this universe is sufficient to answer those questions. So I don't know whether we'll ever know the answers to them or not, but I want us to keep asking, because the instant we decide we can't figure it out and we give up the search, we'll be right. And I don't want to be right like that. I want to keep trying until we know everything there is to know that's knowable. And I think that's a good place to stop, because I'm guessing you have some questions now or some things you're curious about.
Before we have questions, would everyone turn on their camera and unmute for a second and say thank you, however you want to say thank you? I'm going to clap. That was fabulous. Fabulous.
Oh,
Thank you.
cool.
Thank you.
Thank you.
I can tell you right now, Ethan, that I'm glad I recorded it, because I know there's going to be students who ask me to rewatch this with them slower and stop and talk about it, which we will do, and we'll probably generate a list of, I know we'll generate a list of questions I can't answer. Questions though from the crowd, go ahead.
All right, I see the first one from Gavin is, how can redshifting make light lose energy? Shouldn't the energy be conserved? And oh, you've learned about the conservation of energy, which is awesome, because the conservation of energy applies in lots and lots and lots of circumstances. One of the things you learn in physics is that there is a deep connection between conserved quantities and symmetries, right? So you have certain things that are conserved because you have certain symmetries that are obeyed. For example, if I have time translation symmetry, right, which means I can start now and then I can come forward, and I can't tell the difference between then and now, that's where I get conservation of energy from. If I have boost invariance, which means like relativity, like, okay, like I could be at rest or I could be in constant motion and the laws of physics are the same. I get conservation of momentum out of that. This is great on Earth. This is great in a laboratory. This is great when we smash particles together. All of these things are conserved. But in the expanding universe, we do not have time translation symmetry. That symmetry is violated because the universe in the past was smaller than it is now. And in the future, it will expand and be even bigger. So what does that mean for energy conservation? It means that energy is not conserved in the expanding universe. Even worse, and I don't usually tell people this, but why not? It means that energy is not defined in the expanding universe. This is an interesting thing in general relativity. It's only possible to define energy in spacetimes that are time translation invariant. So if it was the same space-time structure in the past as it is today, as it'll be in the future, then energy is conserved. But in the expanding universe, it is not. The only way I know of to look at it, and this is not correct, but I'm telling you, this is how I look at it. If I'm like, no, I'm going to demand that I make a definition of energy that is conserved in the expanding universe, I can ad hoc one together. It's not a valid definition, but what I would do is I would define it in such a way that just like if you blow air into a balloon, the walls of the balloon, as the balloon expands, it only expands because something does work on the balloon, right? You might remember work is force over a distance. So you blow air in, it exerts a force that pushes it out a distance. If I define energy to behave in that way, then I can say, oh, that's what's happening. As the universe is expanding, these photons, the light is expanding the universe. It's doing work on the universe, and that's why it's losing energy. And then you would ask, oh, well, if the universe stopped expanding and it started contracting again, does that mean it would do negative work and my photons would blue shift and get shorter wavelength instead? And the answer is yes. The same made up definition that works for redshift works for blue shift too. But the real explanation is no, this is not a time symmetric universe. This is a universe that changes with time, so energy is not conserved in it. So, shouldn't the energy be conserved? The answer is only if you have a universe that doesn't change with time, and ours does. So you got the correct answer, and then you got the, all right, but what if I don't like that answer? You can make a different one up.
All right, thanks. That's really
Yeah.
interesting.
All right. I see Adam has asked, are stars more massive towards the galactic center? And this is kind of interesting because the answer is you find the most massive stars where you most recently had the largest regions of star formation. So if I said, hey, let's look at this star forming region towards the galactic center. Yeah, I'm going to find lots of massive stars in there. But in the whole local group, the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and about 60 other itty bitty dwarf galaxies, the largest stars we know of are actually in the Large Magellanic Cloud. This is a satellite galaxy of the Milky Way, about 170,000 light years away. We are a big, massive galaxy. It is a little rinky-dink galaxy. And so, yeah, gravitationally, we pull on each other. But guess what? Like Earth pulls on the moon and the moon pulls on the Earth. We have tides on Earth because the moon pulls on us, and the sea level rises and falls by a couple of meters maybe over the course of a day. On the moon experiences moonquakes, right? Seismic shifts that crack the moon and cause it to rattle every day because of the Earth's tides on the moon. The Earth's tides on the moon are way stronger than the moon's tides on the Earth. And the tidal forces that the Milky Way exerts on the Large Magellanic Cloud are much bigger than the tidal forces the Magellanic Cloud exerts on us. So we have the largest star forming region in the local group because there is a massive cloud of gas that is being pulled and compressed by the Milky Way's tides. It's the largest star forming region in our vicinity. It has about 400,000 new stars in it that have just formed. And the most massive one we found is at the core, I'll give you its address, it's at the core of the Tarantula Nebula, and it is in a star cluster known as R136. R136 has something like maybe 2 handfuls of stars that are more than 100 solar masses, with the largest one being 260 times the mass of the sun. And that is the largest single star that we know of right now. But that's why. The reason is because we exist right now at a moment in time where that specifically in the local group is where the largest amount of recent star formation has happened and is still happening there. There are other places where it's happening, but it's very rare to find a star more than 50 or 100 solar masses. So, we're just getting lucky.
All right, great question.
Thank you.
Yes. one more question from Ryan, and then we're gonna have to cut it off because we are getting a little bit past our time. But
Yeah, it's
Ethan, go ahead
bedtime
and
for
answer.
everyone except teenagers, right?
But yeah, go ahead and answer Ryan's question.
Yeah.
and
So,
we'll call
what
it quits.
predictions about the future of the universe can we make based off what we know about its past? And I will tell you that for most of my life, this was the biggest question in cosmology. Like cosmology, the study of the cosmos, it's a branch of astrophysics. It's what I specialized in. And it was realized that, look, there is this amazing solution to the Einstein equations in general relativity. If you have a universe that is on average the same density everywhere, it cannot be static and stable. It must either expand or contract. And so in the 1920s, when they started observing distant galaxies and measuring the distance from them and measuring the redshift, they were like, oh, that's what's happening. The universe is expanding. It's like having a ball of unleavened dough, like having bread dough with raisins all throughout it. And now the dough is leavening, and all the individual raisins are like galaxies within it, that they all expand away from each other. And the ones that are close will expand away at like a slow rate, but the ones that are on opposite sides, they'll appear to expand away farther. The dough is like space, it's invisible, but the galaxies are the things you can see. So what the goal of cosmology was, is it says, oh, if I measure how the universe is expanding and how that expansion rate has changed over time, then the first thing I can do is I can learn what is in the universe. How much of the universe is matter, normal matter, dark matter, radiation, dark energy, all the different components. And then you can take those values and plug them back into the equation and say, ooh, so now what's going to happen in the far future? What is the fate of the universe? Will it expand forever? Will it asymptote to some maximum distance? You all know what asymptotes are, right? Yeah, high school kids know, grown-ups forget, but high school kids know. You know what an asymptote is. So does it asymptote to some value where, oh, like it's not going to run away, but it's not going to recollapse? Or will it recollapse? Will it reach some maximum size and turn around and end in a big crunch? These were the huge questions of our time for almost all of the 20th century. And then in the late 1990s, astronomers were like, guess what? We have the answer. And guess what the universe is doing? It is none of them. It's like it expands. It's like, I imagine the Big Bang as like the starting gun for a race. And on one hand, you have the initial expansion, expand, and you have gravity tugging to resist it. Who's going to win? And the answer is, it kind of looks like that Goldilocks case. It kind of looks like, oh, I'm going to expand and gravity's fighting and who's going to win? And I don't know. And then all of a sudden, about 6 billion years ago, the expansion just started speeding up again. It was like it was slowing down. And then all of a sudden, these more distant galaxies get farther and farther away from us. And this is because of what we call dark energy. But what this means for the future is profound. It means that, first off, of all the galaxies within the observable universe, only 6% of them are ever going to be reachable by us. If we got in a spaceship with magic technology and could move asymptotically close to the speed of light, you would only be able to reach galaxies that were closer than 18 billion light years away. But the observable universe goes all the way out to 46 billion light years away. And if you went and said, oh, well, I'm going to calculate what's the volume of a sphere of 46 billion light years and what's the volume of a sphere of 18 billion light years, you'd find that the 18 billion light year sphere only had 6% of the volume of the 46 billion light year sphere. So as time goes on, everything that isn't already gravitationally bound together is speeding up away from one another. In the very far future, we will only have the local group. whatever the Milky Way and Andromeda and these 60 rinky-dink galaxies merge into, that's it. If you were born 100 billion years from now, you would have to look trillions of light years away to see the first galaxy beyond the local group. Who would invent telescopes to look for that if the closest one was trillions of light years away? Hopefully someone, because hopefully there will still be species coming of age and coming into existence and being intelligent and saying, I want to know what's out there. And what, am I just going to give up because the thing that I wanted to find wasn't easy to find? There are pushes, by the way, to do this. There are people who want to stop doing experimental particle physics because the LHC hasn't found something spectacular already. There are people who want to stop building big astronomy telescopes because we can already see enough stuff already. There are people who want to stop looking for life on other planets, stop looking for intelligent life because we haven't found it yet. And for me, that's just motivation to look harder. You have no right to assume that these questions that we have not yet been able to answer will be easy to answer. So I would say predictions about the future of the universe. I mean, we know the fate of everything in the universe. That's pretty profound. But all of that is based on what we've already observed. It's all based on what we've seen as we've looked farther and farther away into the distant past.
Well, my mind is going to be blown for about another week after this meeting. I'm going to be honest.
Well, that's great. That's great.
Yeah.
You telling me, yeah, Ethan, you should. I mean, Dr. Siegel, you should start that YouTube channel, right?
Yes, absolutely.
Absolutely,
Okay.
yes.
Well, I've got the studio lights, so
Okay.
I've just got to get the green screen up and running and get some software figured out. But
We definitely look forward to that.
Yes.
All right. Well, I'll just have to make it happen. The world needs some good information. People need their minds blown more often, and not because some B-list comedian is getting slapped in the face by some actor.
Sure.
Yeah.
Oh, thank you so much, Ethan. That you've always been one of our best speakers, but now that we actually gave you some time,
You gave me a little more time, so I was like, let's make it better.
Let's go. That is amazing. All right. I will say though, as a 59-and-a-half-year-old, it's perilously close to my bedtime. You teenagers still have 4 or 5 hours to go. And we want to let Ethan go. We really, really appreciate it. You can expect to hear from us again in a year or so. Hopefully you can find the time. And if you ever want to run one of your videos past a group of teenagers as a beta testers, just let me know.
Oh, I see some nods. So the nodding heads indicate that like maybe I should actually take you up on this.
Yeah.
So I'll think about it. I won't forget, especially to anyone who's wearing the same awesome colored shirt as me. Like that's a good deal. No more drab colors. It's the Pacific Northwest. We need some bright colors, people. Come on.
Yeah,
the winter is too long.
Winter is too long.
All right.
All right. Thank you so
Thanks
much,
for having me,
everyone, for coming.
Yeah, you guys are free to go. Thank you guys so much for coming. Thank you, Ethan, so much for presenting. This has been amazing, and we'll see you all next week or in 2 weeks.
All right.
Bye, everybody.
Bye, everyone.
Thank you.
Bye, everyone.
Thank you.
Thank
Bye.
you.
Thank you.
That was incredible.